Good morning, everybody. We're going to talk about how you create an image of an object using a curved mirror. And in order to do this, we need to exploit a couple things. One is a particular type of drawing, and that's going to include one of or two of three rays that can be drawn that are easy to track. Remember, every object that is illuminated gives off light in all directions, and we don't have to keep track of all of the rays of light, just a representative sample to see what the divergence is between rays of light, and then your brain processes those diverging rays back to where they seem to have come from. We're also going to need to make a particular type of drawing with an optical axis, a center line for the mirror, and we're going to have to exploit the idea of a focal point. So let's talk about the focal point first. So I'm going to draw a center line for our discussion here because we're going to get geometrical. And I'm going to draw a mirror, and the mirror is going to be over here on the right, and it's going to be curved in this way. Okay, so we're going to put our object over here on the left. The light is going to go and it's going to hit this mirror and it's going to bounce off. And it's going to form, as I showed you before, it's going to form a focus. The light is going to focus. What am I saying? So let's do that. I'll use the red and the blue again. And let's draw some representative pieces of light. First of all, one of the really easy ones to draw would be a ray of light that is right along this center line, which is actually called the optical axis. The optical axis is the center line for the mirror. It's the place where the mirror's normal for a ray along the optical axis would be right back along the optical axis, so that ray is going to bounce straight back. Then let's choose a ray that's up high, another ray that's down low. And I'm trying to draw these all as parallel as I possibly can, but I don't really care where they hit. And as it turns out, the normal changes directions at various places such that when this ray bounces off, it's going to bounce off and it's going to go probably right about here. And this ray is going to bounce off with a slightly shallower angle and it's going to go right through here. And all three of these rays, the one that bounces straight back along the optical axis, note there's a lot of lines along this optical axis, and the two that bounced off and went here, they all come together right there at a place called the focus. Focus is usually abbreviated with a lowercase f, and the distance between the lens and the focus is called the focal length. Anybody who's played around with cameras and stuff has probably looked at lenses that have different focal lengths, and that determines what their magnification is. Now, another very interesting point is that the focal point for a spherically curved mirror is halfway between the mirror and the center of curvature, where you'd have to put the point of the compass in order to draw this arc. The focal point is halfway between. If you use a parabolic shape of a mirror, first of all, you get a better focal point, but it's not quite the same relationship. So because they're easier to manufacture and because of this nice geometry, a lot of times we use a spherical suction mirror. Now, this type of mirror here has a special name. This is called a concave mirror. And parallel light coming into a concave mirror focuses into a point. This is really important. This principle got used for a device that I saw in the back pages of Popular Science one time called the solar hot dog cooker. It was a device that you could take to your tailgate parties, and it had a big reflector that was curved and then a fork that came out, and you would be able to put onto the fork a hot dog, and then you would point the reflector at the sun, and the sun's rays would come in and be focused at a point and cook your hot dog. Also, there was a board group of college students about 2 decades ago who created something called the solar death ray, which was a bunch of mirrors that they glued at the right angles, and then they could put a basket here and put various objects in the basket and then point it towards the sun, and the object would get melted by the sun. Fun times. So this is a concave mirror. It's got a focal point that is inside of the radius of curvature of the mirror, and that's because the center of curvature is over here. So halfway between is on this side. What would a concave mirror do to an object that was very far from it? So let's draw an optical axis across the page here. And let's put an object, let's put the mirror over here. Slightly curving mirror. And so I'm going to put the focal point right about here. And we're going to put an object I'm going to draw a candle, although at some point I'm going to get tired of drawing these candles, and I'm just going to draw a little arrow. And let's figure out where the image of this candle would be if the light goes into this mirror and reflects back. By the way, this shape, this concave shape, is like the inside of a spoon. So if you get yourself a big serving spoon and you hold it far away from you and you look into the spoon, if it's sufficiently reflective, you're going to see your own image and something will happen to it, something we're going to find out right here. Now, in order to do this, we're going to draw ray number 1, ray number 2, and ray number 3. I'm going to draw all 3 of them this time, and we're going to see if they work. Now, ray number 1 starts life parallel to the optical axis, and then when it reflects, it goes through or in line with the focal point. I'm going to say through because sometimes it doesn't make sense for the light to bounce and go through the focal point. Maybe it goes away from the focal point in some sort of line with the focal point. Ray number 2 is very easy to remember. It's exactly the opposite. It begins life through the focal point, and when it bounces off parallel to the optical axis. And those 2 are enough to find the image of anything. In fact, I tend to just use ray number 1, ray number 2. Ray number 3 is an extra ray you can use if you have trouble, and that ray is going to go from the object. It's going to go straight to where the optical axis hits the center of the mirror. So toward center, and then obeys the law of reflection because, of course, the center line has the optical axis as its normal. So if a ray comes down at an angle here, it's going to bounce off at the same angle on the other side. The reason why ray number 3 is harder to do is it's just not as easy. Now, I'm going to use blue for ray number 1, green for ray number 2, and red for ray number 3 just to keep things straight. So ray number 1 begins parallel to the optical axis. So we're going to take light from the candle. That's the part that's giving off the light. And I want to see that that's parallel to the optical axis. That looks pretty parallel. And we're going to draw that line, and it's going to hit right there. Okay, so that's light that's going. Now, when it bounces off, it's going to bounce off, and it's going to go towards the focal point. In fact, we saw up here, that's exactly what it does. It goes through the focal point. So I'm going to go ahead and take this line and draw it all the way over there to the other end of the page. I don't know where this is going to intersect with the other ray, so I have to kind of do that. Ray number 2 starts through the focal point, so we're going to go from the source of light through the focal point and then continue on to hit the mirror. And then whenever that hits, it's going to bounce off parallel to the optical axis. Does that look pretty parallel? Sure does to me. And we can already see that these guys cross right here, that if your eye was over here and you were looking towards this situation, you would pick up ray number 2 and ray number 1. They would be diverging. Your brain would process them back and say, aha, they were together right here. But just for excrement and giggles, let's see what ray number 3 does for us. Ray number 3 is going to be between these 2 because it has to not hit the focal point. It has to hit here. So we need to kind of split the difference, hit there, and that's a very shallow angle that I have to come out at. Now, I could cheat and just put it right through here because I know that's where it's supposed to go, but let's just make sure that it looks reasonably like that's what it would do. And ray number 3 sure as heck looks like it goes right here. So what does the image look like? Well, the candle, the bright part of the object, is down here. And here's a little known fact. The base of the object is on the optical axis, and all light going on the optical axis stays on the optical axis. So the base of the candle is on the optical axis. So what we have is we have an upside down short little candle right here. And if you look into the back of, the bowl of a spoon held at distance from your face, you will see that you look smaller and you look upside down. So there are some words that are used here. First of all, this is, you can either have an upright or inverted image. In this case, because the crossing happened below the optical axis and the object was above the optical axis, we have inverted. Beep. And then you can have larger, smaller, and sometimes you get the same size. And in this case, it sure looks like it's smaller. Now, in the middle here, there's one more term we can use. You can have a real image, or you can have a virtual image. In this case, it's a real image. A real image is one where the light rays really cross. Okay? Your brain does not have to trace the rays back to some area where the light really never existed, but your brain thinks it did, like with the plane mirror in the last video. And we're going to show plenty of examples of a virtual image. But a real image is where the light rays really cross. The one advantage of a real image is not only can you see it with your eye, but if you were to stick a small piece of paper right here, there would actually be a picture of a candle projected onto that paper. I'm going to say that again. A real image where the light rays really cross is the only image that can project something onto a piece of paper. The light from the candle will bounce off the mirror and focus again on the paper, and you will see an upside down candle on the paper. It's a little hard to do with a spoon, but I've got a big mirror in the classroom that I usually use for this demonstration. Okay, what's important on this page before we move on is that there is a focal point for curved mirrors, that it is halfway between the center of curvature, where you would have to put the point of the compass in order to draw the arc of the mirror, and the mirror itself, and that we draw an optical axis, and we use ray number 1, 2, and 3. Parallel to the optical axis, then through the focal point, then parallel, or towards the center and bouncing off, obeying the law of reflection. Let's try another one. Let's take that same spoon and let's get closer to it. So this is going to be a concave mirror, but I'm going to put the object inside of the focal point. Now, things are going to get a little crazy. So let's draw the mirror right about here. Slight curvature to it. We'll put the focal point right about here. And I'm going to draw, let's dispense with the candle. Let's just draw an arrow. We're going to keep track of the tip of the arrow, just as if that was the flame of the candle. Okay, ray number 1 in blue begins its life parallel to the optical axis. And when it hits the mirror, it bounces off through the focal point. This has not changed whatsoever. That is ray number 1. Ray number 2 begins through the focal point. Okay, if we go from the tip of the arrow through the focal point, we're never going to hit the mirror. That is not appropriate. What we want to do is we want to be along this line, but we need to go hit the mirror. So we're going to go ahead and go this way, away from the focal point, hitting the mirror up here, and then we are going to turn and go parallel to the optical axis. This looks roughly parallel to me. Now, if your eye was out here looking at this mirror, ignoring the object that you can clearly see in front of the mirror, but just looking into the mirror, you would see these two rays, and they would be diverging from each other, but they never actually cross. Your brain, however, would say that these rays appear to have come from some place behind the mirror. So let's trace these last two rays, ray number 2 and ray number 1. Let's trace them into the nether region behind the mirror. Now, if I knew this was coming, I could have made these dotted lines while the ruler was down, but I wanted to share with you the joy of discovery. Oh my! These two rays appear to have come from back here. And if those two rays are the image of the tip of this object called an arrow here, then the tip of the arrow is way up here. The base of the arrow is on the optical axis, so the image of the base of the arrow is on the optical axis. And we are looking at a larger, we are looking at an upright, and we are looking at a virtual image. And now is your time to shine. Go and get that spoon and put it very close to your face. Close enough that you can see it, and you will see that you are right side up and magnified. In fact, some of you even have a mirror in the bathroom that is slightly curved in this way, the makeup mirror. One of the things I like about going to hotels, I don't have a makeup mirror at home, but when I go to hotels, they often have one bolted to the wall, and I get to really inspect my face for defects, and one might say that I don't need a magnifying mirror to do that, but it is kind of fun to do. So this is the image when you are close to a concave mirror. Well, you might say, naturally, what the heck, Harmon? What does a convex mirror do? What does the other curvature of a mirror do? Okay, let's find out. Let's go ahead and have the mirror be curved the other way. Now, for this mirror to be curved the other way, the focal point will have to be on the other side, right? The center of curvature, where I might put the compass to draw this arc, is over here. The focal point is always halfway between the mirror and the center of curvature. The focal point's over here, but I'm still going to put my object over here. In fact, let's make it a little taller. There we go. You can go with the candle. You can go with the arrow. Your book does an arrow, so I'm doing an arrow. But let's do ray number 1 and ray number 2 and see what happens here. Ray number 1 begins life parallel to the optical axis. That right there looks pretty parallel to me. Oh, gosh. Golly, I didn't mean to do that. It does not penetrate through the mirror. It bounces off the mirror. And when it bounces off, well, it doesn't go through the focal point, because that would mean it would go through the mirror, and light doesn't go through mirrors. It bounces off mirrors. But this is the line along which it will bounce off. It will bounce away along this line. And because I'm smart, I'm going to put the dotted line in now. I happen to know that this is going to be a virtual image. I might need to trace it back. So there's your dotted line. Okay, so ray number 1, parallel to the optical axis, bounces off through or in line with a focal point. Ray number 2, excuse me, I haven't had my coffee yet. Ray number 2 begins life on its way to the focal point. This ray is never going to make it to the focal point because there is a mirror in the way. And when it bounces off, it is going to bounce off parallel to the optical axis. Now, maybe I should look at the optical axis. There we go. We'll use the ruler the other way. I didn't know you could do that, huh? Okay, ray number 1 up top, ray number 2 right here, and if your eye was over here, some distance away, looking into this mirror, not at the object directly, but looking into the mirror, you would see these 2 rays, and they would appear, this ray and that ray, would appear to have come from someplace back behind the mirror, right about there, meaning that the tip of the arrow is right at this intersection. The base of the arrow is on the optical axis. This is also an upright image. It is smaller, and it is virtual. This is the type of mirror that people use like on the passenger side of your car to give you a wider field of view, but unfortunately it makes everything in it look smaller. So they have to print a little warning. Objects in this mirror are closer than they appear, because if you're going to use perspective to guess how close that car is, you're going to be incorrect. By the way, in the movie Jurassic Park, when the T-Rex was chasing the Jeep, they had a little fun with it. They showed a mirror, and I don't know whether it was a passenger or driver's side mirror, and they changed the words to say objects in this mirror are larger than they appear, not closer. So that was kind of fun. This kind of mirror doesn't matter how close or far you are. Obviously, you're not going to be able to transition past the focal point if the focal point's on the other side. This kind of convex mirror always produces a smaller image, and it is always virtual. You can't project anything with this. And again, the trade-off for having a smaller image is usually you get a wider field of view. People put these on the corners around buildings so you can see if there's a car coming the other way. Sometimes they use them in stores to allow the associates at the store to check on people and make sure they're not trying to pull a Winona Ryder and stuff a dress in their bag or something like that. So this is how image formation happens with mirrors, and next lecture we will talk about refraction and lenses and do image formation. There will be the same rules, the same 3 rays, and again, you only need 2 of them. I find ray number 1 and ray number 2 to be the most useful. Ray number 3 requires a little more art to it, but it's always there for you. Also, by using 2 rays, you always get a good intersection. When you use 3 rays, sometimes the error associated with your drawing means that they don't all 3 intersect in the same place, and that might not help your confidence in this. So I would say any 2 lines cross at a single point. Let's use ray number 1, ray number 2. Okay, we learned a lot today. We got concave and convex mirrors. We learned that the concave mirror works 2 different ways. When you're far away, it produces an inverted image that's real. When you're close, it produces a upright image that is virtual, and that the convex mirror has its focal point on the other side and produces a upright image that is always smaller and virtual. All right, guys, moving on.